So this section is all about basically counting. It's combinatorics. So I'm sure everybody knows how to count, but this is all about how we can count like large numbers of things. So back earlier in the year, we talked about passwords. That would be passwords is kind of an example of where this principle comes into play. All right, so let's just go ahead and get to it. The fundamental counting principle says that the number of ways in which a series of successive things can occur is found by multiplying the number of ways in which each thing can occur. So, and that's, I guess that should be a can occur right there. Um, so a pizza can be ordered with 3 choices of size, 4 choices of crust, and 6 choices of toppings. How many different one-topping pizzas can be ordered? Well, that's going to be 3 choices for size, 4 times 4 for our crust, times 6 for our toppings. So I get 4 times 6, 24 times 3 is 72. You are taking a multiple choice that has 6 questions. Each of the questions has 3 answer choices with 1 correct answer per question. You select one of these 3 choices for each question and leave nothing blank. In how many ways can you answer the questions? So I got 3 options for the first question, times 3 options for the second, times 3 for the third, for the fourth, fifth, sixth. So that's 3 to the sixth, which is, let's see, 3, 9, 27, 81, 243, so 729. So license plates in a particular state display 2 letters followed by 3 numbers, such as JM126 or ET522. How many different license plates can be manufactured? So if we assume that we can repeat letters and everything like that, that would be, a lot of times when I'm doing this, I'll kind of write it out like this, kind of as far as I'll have my blanks. And I'll think I have 26 options for that first blank, 26 options for that second blank, and then let's assume you can be 0, 0, 0, 0, so that would be 10 options, 10 options, and 10 options, because 0 through 9 for each of them. So it'd be 26 squared times 10 cubed, which again, if we just break out our calculator here, (26 squared times 1,000), so 676,000. So 676,000, 676,000 possible license plates. So you can kind of imagine why California might have more digits than, say, like Montana or something like that. So you're coaching a little league team and have 13 players and need to choose a batting order with 9 players. How many batting orders can you form? All right, so now let's assume that you can't repeat, right? If once you pick a person to bat first, they can't also bat second. So in doing that, we're going to have 9 spots that we have to fill. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And we have 13 options for the first one, 12 for the second, 11, 10, 9, 8, 7, 6, 5. So if we break that out on our calculator, 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5. So we end up with 259,459,200 possible. You can see how this quickly gets really, 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 really big as far as these permutations, or I guess we haven't really talked about them, but how many different ways we can do that. So each batting order is called a permutation of 13 items taken 9 at a time. So a permutation is an ordered arrangement of items that occurs when no item is used more than once. So like that's here we could reuse letters and numbers, right? We had 5, 2, 2. So that is not a permutation. Here we could, in number 4, we couldn't use the same batter more than once, so that's a permutation. And then the order matters, all right? So it's different whether, whether a person's batting leadoff or batting cleanup. Those are two different spots. So order matters in that scenario. So here was our calculation that we did. Well, if you think about it, we could look at this as keep on going times 5 times, and then if we add times 4 times 3 times 2 times 1, if we multiply that on the top and the bottom, we get the same answer. So we can look at this, and now that's the same as 13 factorial over 4 factorial. And where did this number come from? Well, we started at 13 and we counted down 9 people, leaving me with 4 people left. So that's where that 4 comes from, which is 13 minus 9. So we replace the number of permutations of 13 items taken 9 at a time with the notation NPR, where the N and R are subscripts and the P is on the main level. So the number of possible permutations if R items are taken from N items is NPR, which is N factorial over N minus R factorial. And we can do that on our calculator. Instead of doing all this, I could have done math, or actually I could have done 13, then gone to math, PRB, NPR, 9, and notice I get the same answer. All right, so a corporation has 7 members on its board of directors. In how many different ways can we elect a president, vice president, secretary, and treasurer? So those are different positions, right? If there's a difference between me being the president or me being the treasurer, those are 2 different ways to pick them. So the order matters, and I guess we're assuming that we can't have one person do multiple roles, right? We can't have a president also be the vice president. So in this case, we would do 7P4. Again, if we do that by hand, that's just basically going to be 7 times 6 times 5 times 4. Basically, I start at 7 and I count down 4 numbers, 1, 2, 3, 4. And so I get, 30 times 4 is 120 times 7, 840. Or I could do that on my calculator. 7 math, PRB, NPR, 4, and I get 840. And how many ways can 6 books be lined up on a shelf? Well, this is just, we're taking all 6 at a time. So you could think of it as 6p6 or just 6 factorial. And again, if I want to do that on my calculator, I just do 6, math, PRB, number 4 is the exclamation point, so 720. Let's say that I have 3 Tootsie Rolls to give out to students in this class. The night before, I randomly choose 3 students and write their names down. Does the order I write their names down matter? Well, again, does it matter if I give it to student A, B, and C? Is that different than giving that to students B, A, and C? Well, no. The same 3 people get the same Tootsie Roll, or get a Tootsie Roll. So it doesn't really matter what order I pick them. So this is called a combination, where order doesn't matter. So it's basically exactly the same rules as a permutation, but except the only difference is that order does not matter. So order matters for permutations. It does not matter for combinations. For each of the following problems, explain if the problem in one is. I'll have to fix all these typos at some point. One involving permutations or combinations. How many ways can you select 6 free DVDs from a list of 200 DVDs? Okay, so does it matter which order I pick them? No, the order doesn't matter, so that'd be 200 C6. So that's combinations. In a race in which there are 50 runners and no ties, in how many ways can the first 3 finishers come in? So there it's different getting first place or getting third place, so order matters. So that would be permutations, so that would be 50P3. So consider the letters A, B, C, and D. If you choose 3 letters and order matters, you would get all these 24 permutations listed here. But notice each column, this column only deals with A, B, and C. This only has A, B, and D. This one only has A, C, and D, and this one only has B, C, and D. So the calculation, you can kind of see that, oh, well, how many ways can I reorder A, B, C? Well, there are 3 letters there, so there are 3 factorial ways I can order A, B, and C, right? So What's 3 factorial? That's 6. And that's how, again, 1, 2, 3, 4, 5, 6. So there are 6 different ways of reordering the same 3 letters. So if order doesn't matter and we want to get back to just these are the 4 different groups I could have if I'm using combinations, then I would just divide by 6 or 3 factorial. And so basically what I'm going to do is if I'm taking something, a bigger number, I don't want to list them all out. Well, let's just say I'm choosing 5 items. What I'm going to do is I'm going to divide by 5 factorial because that's how many ways I could reorder those five items. So, and this should be an R here. So it's n factorial over r factorial n minus r factorial. And that is the same formula as the binomial coefficients. So NCR you could get from Pascal's triangle if you wanted to. So it's exactly the same as n over r. From a group of 10 physicians, in how many ways can 4 people be selected to attend a conference on acupuncture? So again, order doesn't matter. So in this case, it's going to be 10C4. So I can go on my calculator, 10, math, NCR, 4, and I get 210. How many different 4-card hands can be dealt from a deck that has 16 different cards? Again, it doesn't matter what order I get the cards in my hand. It's just what I have at the end. So order doesn't matter. So it's going to be 16C4, which is equal to 1820. And so last thing I'll say is kind of a nice example to illustrate the difference here is I might say, 10 people race. How many ways can I distribute let's say a gold, silver, and bronze medal. So that's A, bronze medal, and B, 3 top 3 finisher medals. So in this case, gold, silver, and bronze, who gets first, who gets second, who gets third gets a different prize. So order matters, so that's 10P3. And here, the top 3 finisher medals, basically there, it doesn't matter whether I got first or third, I get the same medal. So that's going to be 10C3. So that's kind of a nice way of illustrating the difference there.